Flame On Torch is an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. Combustion reactions are rapid oxidation reactions. One usually burns a fuel, typically coal, oil, or natural gas, in air, or rarely, pure oxygen. The principal atomic species in combustion reactions are carbon, hydrogen, sulfur, and oxygen. There are obviously many other species that burn, and if you get into rocket fuels or other things of that nature, you may have to deal with some of these or other species as well. However, when chemical engineers talk about combustion, they're almost always talking about common fuels, and these days, even with the increase in sustainable energy sources, those tend to be coal, oil, or natural gas. Let's start off by listing some definitions. First off is complete combustion. If all of the fuel is completely oxidized, we have complete combustion. For the principal species, the combustion products for complete combustion are CO2, H2O, and SO2. We don't count SO3 because it takes special techniques to form sulfur trioxide. Next is partial or incomplete combustion. If not all of the fuel is completely oxidized, or if some is not oxidized at all, we have partial or incomplete combustion. The typical product of incomplete combustion is CO. In many major cities, especially in Southern California, any unburned hydrocarbons that are exhausted into the air tend to react with locally produced particulates and create photochemical smog, so incomplete combustion is a problem. Next is stack or flue gas. The combustion products along with any remaining reactants are referred to as a stack gas or flue gas, so called because they flow out of the exhaust stack or chimney flue. The composition of the flue gas is reported in one of the two bases. It's either reported on a wet basis, which means that the water vapor in the flue gas is included in the composition. If the flue gases exit at high temperature, then the water will not condense out and it contributes to the gas flow. Or it's reported on a dry basis, also known as an ORSAT analysis. A dry basis does not include the water vapor in the flue gas composition. So basically, you take the total molar flow rate and subtract from it the molar flow rate of water, and use that as the basis for calculating your composition. One apparatus for measuring flue gas composition was named after ORSAT. In case you haven't guessed, it does report compositions on a dry basis. Finally, relative, absolute, molal, and percentage humidity. Wet and dry bases may make you think in terms of the humidity, or what the humid content of the stack or flue gas is. Well, at the moment we're going to ignore the subtleties of humidity, but when we get to the O. Henry video, we will discuss humidity and how to calculate it in some details. We'll visit it again when we get to psychrometric charts. Here we have a brief example of wet and dry bases. Let's suppose we have 125 moles of combustion gases, 10 moles of propane, 5 moles of carbon monoxide, 5 moles of carbon dioxide, 25 moles of water vapor, 5 moles of oxygen, and 75 moles of nitrogen. To calculate the mole fraction or composition on a wet basis, we include the water vapor. We divide the moles of a species by the total of 125 moles, so on a wet basis we get 8%, 4%, 4%, 20%, 4%, and 60% respectively. On a dry basis, we don't count the water in either the total moles or the composition, so we have 125 minus 25 moles, or 100 moles total. The mole fractions or composition comes out to 10%, 5%, 5%, not applicable for the water vapor, 5%, and 75% respectively. Air is just air, right? Well, if you're going to do a good job of describing air, you have to look at a lot of things. Dry air contains nitrogen, oxygen, argon, carbon dioxide, hydrogen, helium, neon, krypton, xenon, and a lot of other trace gases. Obviously, wet air also contains water vapor. If you want a detailed list of the components in air, search Wikipedia for atmospheric chemistry, and you will see a lot more than you ever wanted to know about air. For DOFPro combustion calculations, we will simplify this list and simply say the dry air is 79% nitrogen and 21% oxygen. Because air is a gas, the composition is on a mole basis and not a mass basis. Theoretical air is the same as stoichiometric air. It's the amount of air containing stoichiometric oxygen needed for complete combustion. I don't know why they call it theoretical air instead of stoichiometric air, but they do. Excess air is calculated in the same manner as any excess reactant. It is a fraction above stoichiometric. Burning in excess air does not guarantee complete combustion, but obviously it's impossible to get complete combustion with less than theoretical or excess air. Burning with less than theoretical air is known as burning rich, as in fuel rich. Burning with excess air is known as burning lean. I know no one does anything with cars anymore, but in the old days, students often understood adjusting your carburetor to burn rich or to burn lean. By the way, all gasoline-powered cars these days burn rich to keep the combustion temperature down, which avoids generating nitrous oxides. They then get rid of the unburned hydrocarbons by use of a catalytic converter. The takeaways for this video are: 1. The principal species for combustion reactions are carbon, hydrogen, sulfur, and oxygen. 2. The products of complete combustion of the principal species are carbon dioxide, water, and sulfur dioxide. 3. Theoretical and excess air are calculated by treating the oxygen in air as a stoichiometric or excess reagent. 4. Excess air does not guarantee complete combustion. 5. The composition of combustion gases are reported on either a wet or dry basis. Thanks for watching. This video was brought to you by the DOFPro team.